The warm-up here was going over the notes that we took last Thursday on square root functions. So we did that warm-up, went over it, and then y'all did the formative assessment over this, okay? And you got to look at your results on that formative. Then we started these notes. We talked about the vocabulary. Remember, this is called the radical. What's underneath is the radicand. And the number here is the index. And if there is no number written there, it's understood to be a 2, which makes it a square root. Okay, we talked about how many possible roots you should get depending on if the index is odd or even and the radicand positive or negative. And then we just did a little refresher on simplifying radicals, okay, which we had initially done this topic back in January when we came back from winter break. Okay, so if you'll flip over to the back, we're going to look at rational exponents. Okay, so remember, a rational number is a number that can be written as a fraction. Okay, so when you have a rational exponent, we're talking about exponent. Your exponents can be fractions. Okay, so in this example here, we've got the base is a, and then your rational exponent is m over n. Okay, and radical expressions can be written using rational exponents, okay, and vice versa. So you can go from a radical to a rational exponent or from a rational exponent to a radical expression. Okay, in this case, when you have a rational exponent, the m, the numerator, represents the power in the radical expression, and the n, the denominator, represents the root, okay, or technically the index of the root when you write it as a radical expression. Okay, so you can see here, I could take m is the power and n is the root. So this could be rewritten as the nth root of a to the m power, or it could be written as the nth root of a, and then all of that to the m power. So it doesn't matter if the power is written outside on the radical or inside the radical, because they'll come out the same either way. And you can go back and forth in either direction with this rule, okay? So we're going to practice that in these next examples. So if I have 4 to the 3/2 power, I don't know that off the top of my head the way that that's written. But if I think of that as a radical expression, so I could rewrite it. Okay, so my base is 4. The denominator, 2, becomes the radical, the root. Okay, and it's a square root. You can put the 2 here if you need to visualize that, where that 2 went. But understand that 2 doesn't have to be written. It's an understood square root if no index is written. And then the 3 is the power on that. Okay, so that can be rewritten this way. So I'm going to try and do some color coding here for you. So the, oops. Excuse me. So the numerator, you can see, becomes the power, and you can write it this way or this way. I'm writing it this last way here. So the numerator becomes our power, and then the denominator becomes the radical. So our denominator 2 became the radical. Is everybody good with that? So now I can solve this because I know what the square root of 4 is. What's the square root of 4? 2. And then I can do 2 cubed. What is 2 cubed? No, it's not 2 times 3. It's 2 times 2 times 2. So that's 8. Good. Now, speaking of cubes, y'all, a lot of y'all are pretty familiar with your squares, your perfect squares. Most of you know those, but not a lot of you know your perfect cubes. So I'm going to come on the back of your notes. You have the back side is completely blank. So I'm just going to come to a blank back place, the back page. If you'll flip over real fast, it might be a good idea for you to make yourself a reference table. Okay, and you can make this as big as you want to make it. including as many numbers as you want to make it. But we can have x and then x squared. And then we could have x cubed. And then you could even go up to x to the 4th. And like I said, you can make it as big as you wanted. So you could keep going with that if you wanted. Okay, but take whatever number we'll start. I'll just do the first 5. Okay, but you could keep going and make this table longer if you wanted a bigger reference table. Okay, but you should know all of these numbers squared. 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, and 5 squared is 25, right? Everybody good with squares? So remember, when you get to cubed, then you're multiplying by that number again. So you're taking this squared number times the x. So the x squared times x. So that's still a 1. 4 times 2, that's the 8. That's where that 8 came from. 2 cubed was 8. 9 times 3, that's 27. 16 times 4 is 64. Okay, and then 25 times 5 is 125. Okay, and like I said, if you wanted to keep going and do the 4th power, you could, just so you have a quick reference table here. So this is still going to be a 1. Okay, and then 8 times 2 would be 16. 27 times 3 is 81. 64 times 4 is 256. And 125 times 5 is 625. All right, and so you could go all the way up to like 10 in your table if you wanted to. I just did 1 through 5. You could do 6, 7, 8, 9, 10 and have a bigger reference table on the back of this if you would like. Okay, that's not a bad idea for as you're working these, because you're not as familiar with those cubes and 4th powers, and you could even make another column for the 5th power if you wanted to. Everybody good with that? Okay, so that might be a good idea to have as a reference. Okay, so where were we? Here on number 4, on this example, we have negative 64 to the 1/3 power. So whenever you end up with this rational exponent, when the numerator is 1, remember the numerator represents the power. Does the power of 1 do anything to the function? So you really don't have to write the power of 1. So whenever your rational exponent has a numerator of 1, it's really just the root of the denominator. So in this case, it's the 3rd root or the cube root. Okay, so this is the cube root. Ooh. Try that again. The cube root of negative 64. And again, you don't have to write the 1 power. If you want to, for the sake of your notes right now, you can. But just know, anytime you have a 1 over a number as your rational exponent, that denominator is just, that's the root you're taking. So if it was the 1/2 power, that just means square root. That's the 1/4 power, that just means the 4th root. Does that make sense? All right, now, we said Friday, that when you have an odd index, it's okay to have a negative under the radical, right? If it was an even index, this would be no real solution. But an odd index, you can have a negative under there. That's okay. That means my answer is going to be negative. And then what did we just put on our reference table? What is 64 the perfect cube of? 4. So this is just -4. -4 times -4 times -4 would get us back to that -64. So the cube root of -64 is -4. All right, same thing with number 5. This time the numerator is not just a 1, so we do need to write it. But again, it's a cube root because my denominator is a 3. The cube root of 125. And then this is squared. I'm going to do my highlighting again here. I got away from that. I didn't do it on the last one. So remember, the denominator is the root. And the numerator is the power. All right, so what is the cube root of 125? It's 5. Okay, 5 times 5 times 5 is what would give me 125. And what is 5 squared? There we go. Feel okay about this rule of rational exponents, how you can rewrite them as in a radical expression? Now it works in reverse as well, like we're going to see in 6 and 7. So it's starting as a radical expression. We're going to rewrite it as a rational exponent. Okay, so here there is no index on the radical. So what is it understood to be? 2. So this is a square root. You can put that 2 there if you need to see that. Because remember, the root is going to become the denominator and the power is going to become the numerator. When I rewrite this, so the base is 7, and it's going to be to the 4 halves power, 4 over 2. So then what is 4 over 2? Yeah, 4 divided by 2 is simply 2. I could get this to switch colors. There we go. So I can simplify that. That just becomes 7 squared, which is, and there we have it. Very good. So what would this number 7 be rewritten as a rational exponent? The base is 2. What's going to be the power, the rational exponent? Is it going to be 4/5 or 5/4? Good. The power is the numerator. The radical, or excuse me, yeah, the radical index, the root, is the denominator. Now, I don't know that one in either format. We can't solve that. It's going to be a decimal, so we're just going to leave it at that. But you need to know that those are equivalent to each other. Y'all feel okay about that rule? All right, good. Now we're going to review some of your exponent rules. You may or may not remember them. I don't know how well you remember your exponent rules, but these are the exponent rules here in the middle column that you learned back in algebra, maybe before algebra. You may have learned these in intermediate, like in a pre-algebra class in 8th grade or something. But here's the rule. Here's what it looks like. And then we are going to apply it with rational exponents because the rules still apply even when the exponents are fractions. We still do the same thing. So the product rule says that when we have like bases, okay, we end up adding the powers. If the like bases are being multiplied, that's why it's called product, because we're multiplying these two terms, we end up adding the exponents. Y'all, does that look familiar, that rule? Okay, so we're going to apply it here. If we have 3 to the 3/2 power times 3 to the 1/2 power. Okay, the two bases are the same, 3 and 3, and they're being multiplied. So I'm going to add the exponents. So 3/2 plus 1/2, isn't that 4/2 here? Okay, so that's where this 4/2 came from. So now it's just 3 to the 4/2, which 4/2 is just 2. So it's just 3 squared, which is 9. Okay. The next rule we're going to look at is your power rule. So when you have a base value raised to a power, and then that's raised to another power, you multiply those two exponents. Okay. And it works in both, all of these work in both directions. Okay. So here in this example, we've got 4 to the 1/2 power to the 6th power. Well, the power on the power we multiply. So 1/2 times 6. So that becomes 6/2, which is just 3. So 4 cubed is what? There we go. Good job. Okay, the quotient rule, you should remember when you are, this is like the opposite of the product rule. When you're multiplying like bases, you add the exponents. So when you're dividing like bases, you subtract the exponents. So the numerator's exponent minus the denominator's exponent. So if we try that here, we've got 27 to the 2/3 power divided by 27 to the 1/3 power. So we are going to subtract 2/3 minus 1/3 is 1/3. So we've got 27 to the 1/3 power. What does that mean again? What is 1/3 power the same as? The cube root, right? So if you need to think of this as, there we go, the cube root of 27, that means the same thing. 27 to the 1/3 power or the cube root of 27. What is the cube root of 27? What do you think it is? It's 3. 3 times 3 times 3. Okay, 3 times itself 3 times is how we would get 27. Okay, and you can use that reference table we made on the back to look at that until you get the hang of some of those, until you memorize some of those perfect cubes. So far, so good? All right, then the next one we're going to look at is the power of a product rule. So if we have two terms that are being multiplied, so the product of A and B, and it's raised to the power of M, you can individually raise each of those factors, A and B. You can individually raise each of those to the exponent and multiply them. Okay, and you should get the same answer whether you multiply A and B first and then raise it to the power, or you individually raise them to the power and then multiply. So let's look at this example here. So it says if I have 4 times 25 to the 1/2 power. So this rule says I can individually raise 4 to the 1/2 and 25 to the 1/2. What is 1/2 power the same as? Square root. Raising it to the 1/2 power is the same thing as taking the square root. So 4 to the 1/2 means the square root of 4. 25 to the 1/2 means square root of 25. So the square root of 4 is 2. The square root of 25 is 5. And then what is 2 times 5? 10. Now, what if we had done this by solving inside the parentheses first? What is 4 times 25? 100. And then 100 to the 1/2 power. 1/2 power means square root. What is the square root of 100? 10, right? So that's how you can see these get you the same answer. So it works both ways. Those are equivalent to each other. Y'all feel okay about that one? All right, and then the last one listed here says the power of a quotient rule. So it's a similar concept, but instead of A and B being multiplied, you can see A and B are being divided. So you can do that division first and then raise it to the power, or you can separately raise the numerator and the denominator to that power. Okay, so here in this example, they have 8 over 27 to the 1/3 power. So you can see they're saying, okay, that's 8 to the 3rd power and 27 to the 3rd power. Okay, 3rd power means cube root, right? So what is the cube root of 8? Okay, and what is the cube root of 27? So this reduces to just 2 over 3. Yes, you could have done this differently. You could have tried to, if this was able to reduce, you could reduce that first. Also remember, you could rewrite this as the cube root of 8 over 27. and then understand that it's the cube root of the numerator and the cube root of the denominator. And that's what we did, right? So if you like to see it written as a radical rather than a rational exponent, rewrite it as a radical if that makes more sense to you. Those are equivalent to each other. You can write it in either form. All right, there actually, before we flip to the next page to do some examples, there's one more rule that I just want to refresh you on, an exponent rule that was not listed here. So it is the negative exponent rule. So I'm just going to add it underneath at the bottom of this table. If my stylus will let me. There we go. So the negative exponent rule is, it says if you have a negative exponent, so we'll use a and m again. But let's say our exponent is negative. We have a to the negative m. Does anybody remember how you can make that exponent positive? How you can change that m from negative to positive? Nobody? Okay. So the way that you would do this is right now, a is in the numerator. There's no fraction, right? So it's understood to be over 1. Do y'all agree? So that's what I mean when I say it's in the numerator. There's no fraction, so it's understood to be in the numerator over 1. So what you do, if you have a negative exponent, you move that term in the fraction. So right now, this is in the numerator. So to change that m to positive, I need to put that term in the denominator. So it goes from a to the negative m to a to the positive m if I put it in the denominator. Now, what would be left in the numerator? Is there anything in front of this a, any coefficient here? It'd be an understood 1, so that would just be 1 over a to the m. And it works in reverse. If you have a negative exponent in the denominator, you can move it to the numerator and change it to positive. So you just have to move where that term is in the fraction to change the exponent from positive to negative. So we're going to look at an example as well. So let's say I have 5 times 2 to the negative 3. I'm like, I don't know what 2 to the negative 3 power is, but I can rewrite it as a positive 3, 2 to the positive 3 if I move it to the denominator. And would that 5 move with it, or would that 5 stay in the numerator? That 5 stays in the numerator. Only what is being raised to the power moves. Okay, and what is 2 cubed? So this is just 5/8. Okay, so we'll need that negative exponent rule a little bit later. So I wanted to add that to the list. All right, so we're going to refer to all of these different rules we just refreshed on as we go through these examples and simplify each expression using those properties of radicals and rational exponents. Okay? In number 8, we've got 2 like bases being multiplied. This is product property that I'm going to use because it's 5 times 5. They each have a exponent. So this is going to be 5 times 5. I simplify it and I end up adding the exponents. So 2/3 plus 1/3. Now, some of you are going to need to write each individual step to make this make sense for your notes. Once you start to do this more and get the hang of it, you'll realize, oh, I'm adding those, and you'll just add it in your head. You won't have to write the step of showing them being added, and that's okay. Or you may just say, okay, I know I am adding these, and just put a plus sign there to show that you're adding those. However you prefer to show that work, okay? What is 2/3 plus 1/3? It does simplify to 1. It is 3/3, right? And again, Some of you will need to write 3/3. Some of you will know 3/3 is 1. Okay, so what is 5 to the 1 power? Just 5. No, when you're adding fractions, remember you have to have a common denominator. So adding or subtracting fractions, you do have to remember how to do that. You need a common denominator, which these already have the common denominator of 3. So once you have a common denominator, you're just adding or subtracting the numerators. Okay. So let's look at number 9. Number 9 is going to be the quotient rule because we're dividing. So we've got 2 to a power divided by 2 to a power. So I'm going to condense this to 2. And then those powers are going to be subtracted this time since it was a division. So 4/3 minus 2/3. So what is 4/3 minus 2/3? It is still 2/3. I don't know 2 to the 2/3 power. Okay. I could try rewriting it as a radical to see if I know it that way. What would this be in radical form? Yeah, the third root, because remember the denominator is the root, so the cube root of 2, and then the numerator is the power, so squared. I still don't know that. That's going to be a decimal either way. So either one of those is correct. So this format, you could stop there, or if you rewrote it like that, that's fine too. It'll be a mix. Yeah, you need to know that those are equivalent because that's changing back and forth from rational exponent to radical expression. You have to be able to convert between those two. All right, what about 10? So that used 8 used product property. This used quotient property or quotient rule. This one, when you have a power to a power. So this is power property. So what do you do with those powers? Multiply them. So we're going to do 3/4 times 2/3. So we said when adding and subtracting fractions, remember you have to have the common denominator. You don't have to have a common denominator to multiply fractions. Multiplying fractions, you multiply straight across the top and straight across the bottom. Okay, if you want to reduce first, you can reduce. Like see how I have a 3 in the numerator and a 3 in the denominator? I know that those 3's are going to reduce, and I'm just going to be left with 2/4. If you don't get the reducing, that's okay. Just multiply. 3 times 2 is 6, and 4 times 3 is 12. So 6/12. What does that reduce to? But that's not it. It can keep reducing. What's this? It's just 1/2, right? Whether you started with 6/12 or you did that reducing first and started with 2/4, either way it reduces to 1/2. So that means this is the square root, doesn't it? Isn't that what 1/2 power means? So what is the square root of 9? No, not squared, square root. So we're going backward here. Yeah, so 3. Very good. So far, so good? All right, in 11, we've got 2 different, radicands are different, but the radicals are the same. See how they're both a 3 index? So that's, if I wanted to rewrite that as 1/3 powers, I could. So this is going to be the same rule. I'm just going to scroll up here and show you. This is the same rule as this power of product rule right here. The only difference is instead of seeing it written as power, we're seeing it written as a radical, but the rule still applies. Okay, so it can be combined into a single cube root. Because they are both cube root, we can put them together as 1. So we can do the -16 times 4 together under the radical. What is -16 times 4? So negative 64. Can I have a negative under a radical? Under all radicals, or does it matter if this is an odd or even index? It matters. Yeah. We said at the beginning of these notes, if it's even, we can't have the negative underneath. But 3 is odd. We can have a negative under an odd index. That's okay. So that means our answer is going to be negative. What is the cube root of 64? So this is negative 4. All right, go ahead. Yeah, if this had been a square root of the same thing, you would have no real solution because you can't take the even root of a negative. So there would be no real solution. No, we're not going to get into imaginary numbers. We're just going to say no real solution. Good question. All right, on number 12, similar concept. We've got the same radical index, so a cube root over a cube root. So we can combine these to a single cube root. So that's going to be 192 over 8, and we can go ahead and do that division first. Because 192 divided by 8 does divide evenly. It's 24. Okay, you can do that scratch work to the side if you need to. So we've got the cube root of 24. Now, was 24 one of the perfect cubes on our reference table we made? No, the perfect cubes were 8, 27. So 24 is between those. So this is going to be a decimal. It's not an exact value. But you always check, can I reduce the radical? Okay, remember, we should be able to reduce radicals. We talked about this on Friday again. We said you can make a factor tree to see if you can reduce the radical. If it's not a perfect cube or square, whatever the index is. So what are some factors of 24? Okay, 3 is prime. What are factors of 8? And then 2 is prime, but the 4 can keep going to 2 and 2. All right, so remember, we talked about this on Friday when we reviewed reducing radicals. We said whatever that index is, 3 in this case, we're looking for that many of a number, right? So now we're looking for 3 of a kind. Is there 3 of a number? Yeah, 1, 2, 3. There's 3 2s. So that means that that 2 gets to come out of the radical, but this 3 has to stay under because it doesn't have 3 of a kind of it. So it stays the cube root of 3. So 2 cube root 3 is the reduced form of cube root of 24. Mm-hmm.
I understand like that factor tree, but what happens to the 8? Why don't we do it?
Because we only look, when we're doing a factor tree, we're only looking at the ends of the branches. And the 8 we broke down. So we're looking at what we broke it down to. And the 4 we broke down. So we're only looking at the ends of the branches at the prime numbers. Okay. All right, on 13, let's see, we've got 5th root on both the numerator and denominator. So I could bring that together as a single 5th root and put the 4 over 8 together inside and go ahead and reduce that. What does 4 over 8 reduce to? So that's 1/2. I know right away, and you probably do too, this would be a decimal, right? We're not going to be able to simplify that any further. So we can just leave it in that format. Or how could I write this as a rational exponent? So 1/2 is the base, that's the number. What would the exponent be for a 5th root? How would that be written as an exponent? 1/5, very good. Oh, come on. So that's technically correct as well. So the 5th root of 1/2 or 1/2 to the 1/5 power, those mean the same thing. Still with me? Stop me as y'all have questions. I know a couple of y'all have, that's good. Y'all just stop me, raise your hand, and we can clarify things if we need to. All right, in number 14, we have a power to a power. So what do we do with the powers? We're going to multiply those powers. So this is going to be y to the root 2 times 4 root 2. Okay, now there's 2 ways to think about this one. I'll zoom in a little bit more here. When you're multiplying like radicals, we can multiply what's underneath them. That's like what we just did here, isn't it? We had 2 cube roots and we multiplied them underneath together. Yes, so I could do that with these square roots. I could go ahead and multiply the 2's together under 1 square root. So I could rewrite that. The 4 would still be there, but then I could put the 2's together under 1 square root. Y'all agree? What is 2 times 2? So I have 4 times the square root of 4. What is the square root of 4? So I have 4 times 2, which is, so this is y to the 8th. Okay, so that was one way to think about reducing that power, because you had square root times square root. You can multiply them together under 1 and then simplify. Now this is a special case. Not only are they both square roots, they're identical. The radicand is the same. They're both the square root of 2. When that happens, anytime you multiply a square root times itself, you're just going to be left with that radicand, in this case 2. You can see how we just came out to a 2 there, right? That's because multiplying something by itself is squaring it, isn't it? And squaring a square root, doesn't that just cancel each other out and you're left with just the 2? Okay, so if you realize that, you can kind of jump from this step to this one. If you don't, it's okay. Do those middle steps. All right. Number 15, inside those parentheses, we've got 2 cube roots. So again, we can condense this to a single cube root and put that x to the 5th times x to the 4th together under 1 radical. And it's all still to the -2 power. When you are multiplying like bases, what do you do with the powers? You add them. So what's 5 and 4? So that becomes x to the 9th. Okay. Now I can rewrite the cube root as the 1/3 power, can't I? So this is x to the 9th to the 1/3 power to the -2 power. So when we've got powers to powers, we multiply, right? What is 9 times 1/3? Yeah, 3. And then what's 3 times -2? -6. So this, if you need to break that down instead of going straight to -6, if you want to write this and show that we did 9/3, and then we said 9/3 is 3, and then we did 3 times -2, you can show those steps in between, and we get -6. And actually, I'm going to scoot that over just a tad, because we don't really want to leave a negative in our exponent. So that's why I added that negative exponent rule under our table. Because how can I rewrite that so I don't have a negative exponent? Yeah, Yeah, I move it to the denominator. And that's what it becomes. All right, I'm going to go, y'all stay seated, please, until the bell. I'm going to go ahead and finish 16 here. I'm going to rewrite this as a fourth root. So I've got the fourth root of x cubed in the numerator, and I've got the fourth root of 81 in the denominator. The fourth root, 81, is a perfect fourth. That's 3, because 3 to the fourth gives me 81. So I can leave this numerator as the fourth root, and I can leave that as my answer, or I could rewrite my numerator as a rational exponent. So that would be x to the 3/4 power over the 3. That would be correct as well. Okay, so there's 6 there at the bottom that say you try. So I want you to try those. Okay, and then I'll make a video going over those for you to check them. Okay, tomorrow in class, you're going to be doing some practice over this. Don't forget that Alex from last week is due tonight. Okay, if you don't finish it tonight, you'll be able to finish it in class tomorrow, but it'll be at 80% credit.
Where do you go to find Alex? Can you go to the SSO portal?
To the like Ed.
Yeah, it's the McGraw-Hill
That's
off the SSO portal, and then Alex.
Alex.
Yeah, and if you go on our Canvas in the assignment, I have the pictures of the icons so you know what you're looking for. Y'all have a good day.